morning students. Today we start from potential energy of a dipole in external field. External field means external electric field. Okay, as you can see from the diagram. Okay, so consider a dipole placed in uniform external field. Uniform external field means uniform external electric field. You can see from the diagram. Okay. In diagram, you can see that positive charge experience a force plus QE in the direction of field. Negative charge experience a force minus QE in opposite direction. This distance is equal to A cos theta and this distance is also equal to A cos theta. Dipole moment vector is from negative to positive. Okay. So, in uniform external field, keep in mind that uniform external field dipole experiences no net force. No net force means force is equal to 0 but experiences a torque because the line of action of forces is different. Okay, as we discussed in previous topics, that is tau is equal to P cross E, but you know that the cross product is equal to P E sin theta. Okay, this torque tends to align the dipole along electric field. This torque align the dipole along electric field in this way. Okay. Now suppose an external torque is applied to rotate the dipole from angle theta naught to theta 1. Okay, so work done in rotating the dipole by external torque, that is equal to W is equal to integration theta naught to theta 1 to function of theta d theta, that is equal to theta naught to theta 1. The value of tau is Pe sin theta into d theta, but P and E are constant, so these are taken out. Then we get W is equal to Pe integration theta naught to theta 1 sin theta d theta. Then the integration of sin theta is minus cos theta. Then we get W is equal to Pe integration means we get from this sin theta d theta is equal to minus cos theta. So W is equal to Pe bracket minus cos theta naught to theta 1. Okay. Now take the negative sign out. Then we get by putting the upper limit and lower limit. W is equal to minus Pe bracket cos theta 1 minus cos theta naught. By applying negative sign on this bracket, we get W is equal to Pe cos theta naught minus cos theta 1. Now put theta naught is equal to pi by 2 and theta 1 is equal to theta. We get W is equal to Pe cos pi by 2 minus cos theta. But as you know that cos pi by 2 is 0. So Pe 0 minus cos theta. Finally we get W is equal to minus Pe cos theta. Okay. This work is stored in the form of potential energy, that is U equal to minus PE cos theta. But you know that AB cos theta is equal to A dot B, then PE cos theta is equal to P dot E with negative sign, that is equal to potential energy. Okay. Now a new topic, electrostatics of conductors. This has a number of points. So first point is inside a conductor, electric field is zero. Electric field is zero. For this we are taking the help of this diagram. Okay. As you know that when a conductor is placed in external electric field, then conductor has free electrons. So due to the presence of electric field, as electric field is applied, free electrons experience a force in opposite direction and they are collected on this surface. This process continues till the magnitude and the collection of negative charge on this surface leaves the positive charge on this surface. This creates an internal electric field EP. Okay. This process continues till the magnitude of internal and external electric field becomes equal when the magnitude of E and EP are equal. The movement of electrons stops. In this way the net electric field is zero. This means electric field is zero everywhere inside the conductor. Okay. The second point is electric field must be normal. Means at right angle to the surface of charged conductor. Okay. For this we have this diagram. Suppose E is at theta angle. Okay. Suppose E were not normal. Means electric field were not normal. It is at theta angle. Then it would have tangential component E cos theta along the surface, and if we have the tangential component of electric field along the surface, then free charge on surface would experience a force and move, and when the charge is in motion, then there exists a current, but in real situation there is no current. This means E is not at theta angle. Okay. Therefore E should have no tangential component. Means E cos theta is 0. E cos theta is 0. That is cos theta is equal to 0. This means cos theta is equal to cos pi by 2. Because cos pi by 2 is 0, then we get theta is equal to pi by 2. This means electric field must be normal to the surface. Okay. The third point is interior of a conductor can have no excess charge. Okay, for this, according to Gauss law, closed integral E into ds is equal to q upon epsilon naught. But from first point, electric field is 0. Then q upon epsilon naught is equal to 0. Finally, q equal to 0. Thus, the interior of a conductor can have no excess charge. Means charge is 0. Okay. The fourth point is charge resides. Means charge is on the surface of conductor. For this, we are taking the help of this diagram. Okay. Consider any arbitrary volume V inside a conductor. Okay. Now, on the closed surface, dotted line represents this surface. On the closed surface bounding the volume V, electric field is 0 because inside a conductor electric field is 0 and this volume is inside the conductor. As electric field is 0, electric flux is also 0. Then according to Gauss law, phi is equal to q upon epsilon naught. For phi is equal to 0 means electric flux is equal to 0. We get q is equal to 0. This means charge enclosed by the surface is 0 means no charge. This means there is no charge enclosed by surface. Then the charge resides on the surface. Okay. The fifth point is electric potential is constant. Electric potential is constant throughout the volume of conductor. How? For this, electric field is 0 inside a conductor. This is from first point. So, no work is done in moving a charge inside a conductor because no electric field. So, no force is present. Then, work done is 0. Then, if work done is 0, then there is no potential difference. When there is no potential difference, then potential will be same on the surface as well as in the interior of conductor. Okay, we know that electric field is equal to dV upon dl. Potential gradient of length. Then since E is equal to 0, we know E is equal to dV upon dl, but E is equal to 0, then dV upon dl is equal to 0, then dV is equal to 0, and if dV is equal to 0, then V is equal to constant. This means potential is constant. Okay.